And please, whenever you have troubles to understand, because it's kind of tricky, and this is a topic that very often also ourselves, and we realize by teaching it to people think they understood, and they say, yeah, that's kind of easy. And then you realize when you have to do it yourself or you go to the lecture, it's actually not that easy, and people get very confused. So try to really understand and interrupt. We have a lot of time for this lecture. Okay. So this is the outline of this lecture. So first of all, I would like to discuss why retention time information is important at all. And then I would like to discuss with you how we can obtain this retention time information. There is many different ways. And then very importantly, retention times differ when you go from one instrument to the other. So I would like to discuss with you how to standardize retention times and introduce this IRT concept. And then we should discuss a bit more the practical aspects, how we actually do a scheduling or prediction of retention times. And I'd like to show you how Skyline supports IRTs. And I'll finish off with a summary and some outlook and applications. Okay, so why is retention time information important? Let's first of all define what retention time is, or chromatographic retention time. So the retention time is a property of a peptide that is dependent on the sequence of the amino acid residues and on the interaction with the resin. So this will be fixed for every peptide, and this is changing depending on your setup. Here I listed some things that cause variability in retention times. So for example, the autosampler and LC setup. So maybe on my autosampler, it takes 20 minutes to pick up the sample and put it onto the column until I start the gradient. Maybe on your system, it takes 35 minutes because you have a pre-column or something. So already you have a 15-minute shift in retention times. Also, the length of your chromatographic column will influence the retention time. The resin that you're using, so the C18 material, the bead size, the pore size of the C18 material, of course the gradients and buffer composition. So if you run a longer gradient, your retention times will be later, as well as if you use less hydrophobic buffers, for example. The temperature has an impact, then also the sample matrix. So if I inject the peptides in water, it will have a different retention time than when I measure these peptides in a yeast lysate, for example. Also, the loading amount plays a role. So if I inject 1 microgram of my yeast lysate, and if I inject 2 micrograms, the retention time will shift. And then there are, if all these things are controlled and exactly the same, there are still small variations usually in retention time, which are coming from bubbles or pump instabilities that you cannot not really account for. Okay. So, and why do we need this retention time information? So one point was already extensively discussed. It's the scheduling. So when we monitor a certain peptide, not across the whole retention time gradient, but just during a certain time, because we know that it's going to elute in the beginning of the gradient, we don't need to measure it in the end of the gradient, right? So we can actually make use of this knowledge and focus the instrument time on that peptide. And so we can have increased dwell time and increased sensitivity for that peptide if we use scheduling. But the scheduling obviously is only possible if we have retention time information. And the other point where retention times are very important is the identification. And this is not only for SRM, but this is becoming very, very important for the swath data analysis, or in general DIA, data-independent data analysis. There, the retention time information is not meant for scheduling, because there we don't do scheduling, but there it helps us a lot to find the correct peak. And that's what you can see here. This is just an unscheduled SRM run, and we have 2 very nice peak groups. So which one is the right one? Of course, if I know that my peptide is eluting at 16 minutes, then I'm pretty sure that this one is the right peak. So retention time information leads to gain in sensitivity, as we can achieve through scheduling, and selectivity, we are more sure about the identification of the peptide. Okay, so this is the scheduling concept shown in a different way. This time we have here an MS1 map, MS1 feature map. So we have the retention time on this axis and the mass on this axis. And what you can see here are peptide features that elute from the column during a certain time. And you can see the isotopic pattern on the mass, in the mass direction. So unscheduled SRM means that we measure, for example, if we are interested in this peptide here, we just measure the transitions for this peptide during the whole retention time gradient. And if we're interested in this peptide here, we also do that. But you can see it's kind of a waste of instrument time to do this. And scheduling now means that we monitor this peptide just during this expected retention time, and here just during the expected retention time, as well as here and here. So we can achieve more multiplexing without decreasing the dwell time, because we, at the same time, we always measure only 2 peptides, but overall we measure here 5 peptides, whereas here just 2 peptides. So that's the main advantage of the scheduling. And just as Christina also mentioned before, scheduling means to monitor a peptide only during a defined retention time window. And this retention time window, for example, in my case, I usually use plus minus 2 minutes. And if you have very accurate retention times, you can go even smaller, or you can go larger. That's very much dependent on the quality of your retention time information that you have beforehand. So now this, what I said, I usually use plus minus 2 minutes, but you can of course use less or more window size. And this is a graph that comes from Skyline, and you will also produce this yourself from our data set within Skyline. And this graph tells us here the retention time, and at what time of the retention time we have how many concurrent transitions. And my goal is always to have 100 or less concurrent transitions, so that I have an adequate dwell time for each of the transitions. So for example, in this case, I would have to use 2-minute windows to be below 100 concurrent transitions. So that's also what you could see here. For example, if I increase the size of these windows, you can see that they would start to overlap here, they would start to overlap here. So suddenly, instead of just 2 peptides, I would measure 4 peptides at the same time if these windows are a bit bigger. So you can see that bigger window sizes again lead to smaller dwell time. I can spend less time on each peptide because the windows are overlapping. And this graph here shows the quantitative accuracy that is achieved with using different window sizes. So the bigger the window size, as I said, the less dwell time we have per transition. So the worse is the signal to noise. So it's better to use small windows if you have accurate retention time information. Yeah. Okay. Okay, this is what you have seen before, the setup on the instrument. And now let's talk about how we can obtain retention time information. So do you have any ideas? Where can we get retention time information from?
If you identify the peptide.
Pardon?
If you identify the peptide with mass spec.
Yeah, exactly. From discovery-based or shotgun experiments, you can extract the retention time. And synthetic peptides, exactly. So there you could do an unscheduled SRM run and define it. Exactly, just prediction. Yeah, I will show you. Yeah, kind of. Good. Okay. So I have noted here unscheduled SRM from maybe synthetic peptides or even also from endogenous peptides. Discovery-based experiments, so shotgun experiments from databases, and the in silico prediction. So let's have a look at each of these points. So the first is the unscheduled SRM run. So if I have a very high abundant protein and I do an unscheduled SRM, I could hope that I just see one big peak, and this is for sure my peptide of interest. The problem is that you can never be sure. So there might often be confounding peak groups that impede confident peak identification. So, for example, this case, well, you would have to have a synthetic reference peptide, a heavy reference, to be sure which one of these is your right peak. And then, of course, for example, in my case, with the SRM atlas for the whole tuberculosis proteome, these were 17,000 synthetic peptides. If I had measured them all by unscheduled SRM, that would have been way too much work. So I needed to do the scheduled. So this can be very time-consuming if you have many target peptides. So what you also mentioned was the shotgun-based or discovery-based experiments to derive retention time information, and that's indeed what I also did for my MTB libraries. The problem here is that often you go to SRM because your proteins are of low abundance, and you actually might not see them by just shotgun. So you do a fractionation of the samples, and the problem then is that in a fraction of your sample, the retention time will be different than in a wholesale lysate, right? So you have to make sure that you account for the fact, that you somehow are able to normalize. Because if I derive my retention time from a fraction and afterwards I want to use it in a wholesale lysate, it might be very different. So that's just something to keep in mind, but we will discuss how to do that afterwards. And then, yes, also the shotgun runs are typically acquired on a different instrument, which might have a different LC and a different gradient, while, for example, the unscheduled SRM runs are run on the same instrument and the scheduled. So there you could directly take the same retention time, but with shotgun experiments you have to also account for this, and we will discuss this after. The third source of retention time information are the online databases that I have presented this morning as well. So where you download these tables, and if you're lucky, they contain retention time information. And here it is just very important that, often you don't know who uploaded data to this database. You have no clue about the quality, and it's very difficult to find out. Go into the publication and check if you actually believe these retention times, if you think they're of good quality. And you would also have to, some of the databases provide just predicted retention times. So then it's like a hint, but you have to be careful by using it. So it's important to understand what is inside these databases before you use that information. And the last option is the prediction just based on the amino acid sequence. And here the most often used algorithm is called SSR-Calc, Sequence-Specific Retention Calculator. And it basically takes into account, calculates the hydrophobicity of your peptides based on the amino acids. And you can do this on this website where they provide this web interface to do that. But actually, it's much easier to do it within Skyline, and Brandon has implemented this. So you will also do this afternoon and see how this works. That's very straightforward. Okay, but now the very big problem. We have found the retention time. Like, let's say my peptide of interest had a retention time of 30 minutes in my shotgun experiment. What will be the retention time on my SRM machine where I have a much shorter gradient? Or, for example, retention times can be changing when the column gets older or when I have to put a new column. So how can we normalize these retention times? And to make it useful to put a retention time on a database, because it's not useful if you read there 100 minutes. Maybe you want to run a 30-minute gradient, and of course then the 100 minutes doesn't make sense. So how can we normalize and standardize retention time information? So now I would like to introduce this IRT concept. And this has been developed all around a set of so-called retention time peptides, or IRT peptides. And all this concept has been described in this paper, which you can also read. And these peptides are available by Biognosis. That's a company in Zurich which sells this kit. But I will show you afterwards. You can also either synthesize these peptides yourself or use endogenous peptides, but this will be for after. So for now, I explain everything with these 11 IRT peptides. So these peptides you spike into all of your samples at a relatively high concentration, so you will always be able to detect them very nicely. And the most important feature of these peptides is that they elute over the entire chromatographic gradient. So the first peptide would elute very early and the latest peptide very late, so they cover the entire range. And to each of these synthetic peptides, a certain so-called IRT value has been assigned. And this usually goes from 0 to 100, and then the first peptide, which has been added later, has now a negative IRT. So IRT values can be negative, but it's easier to think of like from 0 to 100 plus than that one. Okay, and all these peptides, I mean, the ones that are now commercially sold by Biognosys are non-naturally occurring, so you can spike them into all samples, and this should never interfere with your endogenous peptides. Okay, so now we have these peptides, and the main idea is now that we normalize our retention times relative to these retention time peptides. So for example, this is my peptide of interest. It elutes here at 17 minutes. But instead of saying that my peptide elutes at 17 minutes, I say that it elutes between peptide 1 and 2 at about 60% between the two. And so, for example, in this case, let's say this peptide has an IRT value of 0, and this peptide has an IRT value of 100, then my target peptide would have an IRT value of 60. And this IRT value of 60 is now completely independent of any gradient, right? Because if I again inject my two retention time peptides on a different gradient, still my peptide of interest will be at 60% between these two peptides, irrespective of if it's 17 minutes or 34 minutes. It's just somewhere in the middle between the two and a bit closer to the second one. So that's the main idea of this IRT concept. So now I have this, I know that my peptide has an IRT of 60, and I can now go from this gradient, the small gradient that we had here, which is shown faint, and now I go to a new gradient from 10 to 50 minutes instead of 5 to 25, and I want to convert the IRT of 60, and I can do that and get an expected retention time for my target peptide of 34 minutes. So you can always convert your target peptides into the IRT scale and back. The only thing that you need, you have to have these IRT peptides which serve as a reference. And the good thing is that now, as I mentioned before, these IRT values are completely independent on column, gradient, and everything. They are not in minutes, so they are dimensionless. They are not dependent on some certain time or anything. So they are fixed once and for all. My peptide will always have this IRT value, and they're independent of any settings of the instruments. And so this is just showing these 11 retention time peptides. On the x-axis, you see the IRT value, which is always the same, of course, because this is a defined value. And here you see the actual retention time on many different instruments and so mass spec and LC platforms and different gradient length. And you can see that the relative position of these 11 retention time peptides are always the same, irrespective of what kind of gradient. It's just that the numbers here change, but the relative distribution of these peptides remains the same, and that's of course important for this whole concept to work. So IRTs are independent of LC platform, gradient, central matrix, etc., and they can be stored in databases, transferred between different instrument platforms, and even between different labs. So I can tell you my peptide has IRT 60, and you need to know which retention time peptides are used, and then you can find out the retention time in minutes of that peptide on your own system. And we will do these calculations together afterwards. So the IRT is, in that sense, kind of a prediction of your retention time. And I say prediction because it's not real prediction. The actual value comes from empirical data, but afterwards you can use the IRT to predict what the retention time will be on your new system. And this here compares, this is a prediction based on SSR calc, which is, well, that's what I've shown you before. This is only based on the amino acid sequence of the peptide. And you can see that the SSR calc-based retention time and the true retention time actually correlate pretty well. The spread is about maybe 10 minutes or so it's not very precise, but it's kind of, the overall trend is caught very well. And so this, if you don't have anything else, that's better than nothing. But now with the IRTs, we can obtain a very good correlation between the IRT and the empirical, so that the IRT-based prediction and the empirical retention time. So IRT is much better. So if you have IRT, use IRT, not this prediction. And this is just quantified over here, the difference between predicted and actual retention time, which is much larger with SSR calc than with IRT. Okay, so let's sum this up. The IRT peptides are non-naturally occurring peptides which cover a broad retention time range, and they're spiked into our samples before the injection. An IRT value has been assigned to each of these IRT peptides. The IRT is a fixed number assigned to each peptide, and that's actually where this name comes from, so this means indexed retention time. IRTs are dimensionless, so that's not in minutes or so, it's more like a percentage. It's just 60 IRTs. And the IRTs are always relative to your IRT peptides. So their 60% is meaningless if you don't know 60% of what. Right? So you have to have these IRT peptides as a reference. And IRTs are independent, as I said, of chromatography conditions, so I actually prefer this definition of IRT, independent retention times. And the IRTs can be stored in databases and transferred between different platforms. Okay, and now how are we using these IRTs in practice? How do we do this scheduling? So I noted here all the steps that you have to do if you want to do a scheduled SRM run, and it's kind of conceptually similar what you have to do later on to predict retention times for BIA or SWOT data analysis. So if you understand the scheduling for SRM, the other one will also become clear to you. Okay, so first of all, we run a sample containing my target peptides. So let's see. First of all, we have to find the IRT value of all my target peptides. So for this, I run a sample containing the target peptides and the IRT peptides, and I look at the data in Skyline, and I obtain the retention time of all my target peptides and of all my IRT peptides. And then I use the IRT peptides to establish a linear regression of retention time versus IRT. So let's say, so this is the retention time, and now for my IRT peptides, they have already an IRT value defined, right? And now I measure, in this run, I measure also the retention time. And I get, for all the 11 peptides, I get a curve that looks like this, the IRT value which is given, and the retention time value that I have measured right now in my run. Okay, and now I have this linear regression. And now I can use this correlation between retention time and IRT to convert the retention time of all my target peptides so this is my peptide. So that's my target peptide 1. I can now convert this retention time into IRT space. So now I know my target peptide 1 has an IRT of 60. And this value is now the value that I store in my database. So now I have, for myself, I just have a huge table with all the peptides of MTB. And for every peptide, I have an IRT value. For example, here it's 60. For peptide 2, it will be 78. Peptide 3, it will be 5. So that's all the retention time information that I store. And this needs to be done just once, because, as I said to you before, this IRT value is fixed, and so once you have determined it, you can use it for the rest of your life. And now, let's say a couple of weeks later, I actually want to do an SRM, a scheduled SRM run. So now I take, so basically, now we went through these steps. We made the linear regression. We converted the retention times of the target peptides using the parameters from the linear regression and calculated the IRT. And that's what I said is the final IRT library. And now we do our scheduled SRM. So now what I do, I run my IRT peptides and determine their actual retention time on the current LC system. So again, I measure the 11 IRT peptides. Again, for them, I know the IRT value, and this is now the new retention time on the new system after changing the columns and changing the gradients. Again, I get a really linear correlation. This might be different from this one. If my parameters have changed, this linear correlation will be changing the slope. And now I can, for all my target peptides, now I don't know the retention time of my target peptides because I haven't measured it yet. But I can now use, I know my target peptide 1 has an IRT value of 60. And now using this new linear regression, I can calculate when I would expect my target peptide 1 to elute on this new chromatography system. So I just do the same but reversed. And this is then the information that I feed into my scheduled SRM method. Is this clear? Okay, and the good thing is now, so before, some years ago, we still had to do all this in Excel and calculating regressions and making sure not to mix up X and Y and then. But now all this is nicely implemented into Skyline, so it's very easy to use. And there is this one window which is called IRT calculator. And here you can define all your IRT peptides, so the 11 peptides with their IRT value. And down here, you can put all your target peptides. So for me, again, this is like 20,000 peptides with their IRT values. So in this, you store all this information in Skyline. And then Skyline automatically detects in your run, if you have spiked in the IRT peptides, it will automatically detect these IRT peptides and use them to predict the retention time of all your target peptides on this retention time on this LC system. So it will give you a very accurate prediction of when it would expect your peptide of interest. So that's this one, this thin line with the yellow areas that you can define how big they should be. In this case, like 1 minute or so. And this is very helpful. Here in this case, of course, the peaks are very clear and you don't need any retention time prediction. But imagine you have a lot of peaks and your peptide might be one of the lower abundant ones. Then you are really happy if you have a prediction and you know that here is where you expect your peptide of interest. Okay, so then let's summarize this. So scheduling improves the quantification accuracy and multiplexing in SRM type experiments. And I've shown you that the empirical retention times and IRTs provide better accuracy and more efficient scheduling than the predicted retention times. This was this comparison to SSR calc. IRT is a peptide intrinsic property that is stable across platforms, gradients, sample matrices, whatever. And IRT is therefore a really good solution to store and share retention time information. And then what we haven't talked about now, but you will see it later during the course, this IRT information or retention time information is very, very helpful for the confident identification of peaks in swath MS data types. And as a brief outlook or extension, I wanted to mention that there is this on-the-fly retention time calibration. So some instruments, for example, the thermo, they can do on-the-fly calibration. So you specify before in your method which peptides are reference peptides. And while you are measuring, the instrument or the software is detecting if these peptides elude at the expected retention time. And if it sees, oh, everything is shifted by 1 minute, it will change the method on the fly so that it will be fine again for the rest of your method. So you can do this while you're running, which is actually pretty nice. And it does this by doing a linear fit between 2 preceding reference peptides and use this fit to adjust the retention times of all the following peptides. And then there is another concept that I quickly wanted to tell you. I mean, nobody says that you have to use these 11 spike-in IRT peptides. In theory, you can use all kinds of peptides, and maybe it's even smarter to use endogenous peptides. If you're just working on one, let's say always on yeast, and you know that in yeast always these proteins will be highly abundant and very well detectable, then you can also choose endogenous peptides instead of spiking in the IRT peptides. And so Sarah Parker, she was a guest researcher in our group, and during the time she was there, she established this set of what she calls common internal retention time standards. So it's endogenous peptides that are present in your sample, so don't spike them in. And these peptides are highly conserved. They come from highly conserved proteins, so they should be present in human, mouse, yeast, whatever sample type. And she also included not only highly conserved proteins, but also some common contaminants like, I think, keratins, for example, which are just also always present in our samples, unfortunately. And from this, she defined a new set of IRT peptides with different sequences and slightly different IRT values. But again, these peptides span the entire retention time gradient and can be used for the same purpose, exactly the same as the IRT peptides. And with this, I'm already through. And what I would like to do now, I would like to clean this, and I would like you to tell me how I should set up.
I'll just add one thing. If you start out with somebody else's IRT calculator that's been calibrated to a certain set of peptides, whether the IRT peptides or their own peptides, and you do some experiments and you find endogenous peptides, or you decide you want to spike in new peptides, if you find endogenous peptides for which you already have IRTs, Skyline makes it relatively easy to recalibrate the calculator and say, oh, these are my standards. So you can get, there is a UI for just saying like, oh, you know, before I was using these 10, now I'm using these other ones. If you decide you want to spike in new things, then all you have to do is measure the original IRTs and the new things that you're going to spike in the same sample, and get those new things into an existing IRT calculator, and then go through the process of changing your standards. So again, yeah, you can transfer from one set of standards to another, and still use, you know, if you're doing MTV, you can still use Olga's 20,000 IRT, you know, database if she gives it to you.
Okay, so let's say I have a sample and I have an aliquot of IRT peptides, and I would like to measure, let's say, 10 peptides in my sample in scheduled SRM. So what do I do? How do I have to start? I don't know what the IRT is of my target peptides. Okay, and in what kind of mode? Like, how would you measure? one for unscheduled. Okay, so what do I get out from here?
For IRT, new retention times for your RT peptides to calibrate that calculator. Then you will get RT values for your sample.
Yeah, so I will get for my IRT peptides retention times, and for my targets also the retention times. And for this, in addition, I know already the IRTs, because this is given. So now again, I use this to establish the linear correlation between retention time and IRT. And now I use this linear regression to find the IRT for all my targets. Okay, so this is my database of IRT for all targets. Okay, and now I want to measure in scheduled SRM my targets. What do I do now?
Measure your IRT peptides
One is your ligand, and the other is only
Mhm. Right. Yeah. So I do. Okay, so this was this is a one-time effort, and now what we describe now is what you do always before each new experiment. I measure unscheduled SRM for IRT peptides. And it is important here that the IRT peptides are spiked into the sample that you are actually going to use. Because as I said, if you spike them into yeast or MTB, even if everything else is the same, the retention times will be different for the two sample types. So you will lose one injection for your sample for this purpose. Okay, and then from here I get out the new, for the IRT peptides, I get the new retention time, and the IRT I have already. And again now I use this to establish a linear correlation between retention time and IRT. Okay, now?
calculate. So using the linear correlation, you calculate the rotation time of the
Yeah.
peptide.
Yeah, exactly. Yeah. So from this, I now, for all my target peptides, I know the IRT, so I can calculate the expected retention time. And calculate the expected new retention time. Using this IRT information here and the new linear correlation I just established in one single injection before I start. So usually we do this injection and then we run a Glufic or some standard, and while this you have exactly 45 minutes to calculate the retention times for all my targets, and set up the schedule SRM method, and then I can start to run the scheduled experiments. And what might happen then I mean, then maybe during your experiment you have to change the column or something, or in general maybe you started with a kind of new column and it gets a bit older, the retention time shift again, and then you just go through this adjustment again and again if needed. So to use the same, and you will see it's quite straightforward in Skyline actually to do that, and you can easily export the new updated methods for your instrument. So that you can easily update the retention times in case you see while monitoring your runs that your peaks are moving out of the scheduling window. Good. So do you have any questions regarding this? Yes.
So I remember from tutorial that recommendation was to use more than one round to get IRT values for peptides of interest. So how many rounds do you use normally?
Actually, we use them from one run, so we don't do several runs. I try to do it one. I mean, I just want to have a run where all my, if I can't detect my peptides in a single run, I need more runs. But
and it's stable. So provided that your LC system is stable enough, right? So that's nothing.
Yeah, but you always have the IRT peptides
Yeah.
inside, so if the LC system is not stable, you probably can correct for it with the IRT peptides that you have inside already.
And I find that, for example, in my case, IRT retention time for IRT peptides was really stable, but for my targeted peptides, some of them they shifted ever so slightly, so I would not be able to make like proper IRT values. So
yeah, I mean, of course, always these IRT values come with a certain. I mean, this is also why in scheduling, I don't. So maybe the peak width in SRM is just 30 seconds, but my window will be from here 2 minutes and from here 2 minutes. So I mean, I kind of account for the fact that these peptides might be indeed, this IRT value might not be very accurate, and that my peak would be here, but I will still catch it in my window. So then, if you feel that your IRT values, even though I'm not sure why you have such a variation, but
Well, so every retention time measurement does occur on a distribution. It's probably a normal distribution, and every peptide has a a different tendency with that. How much some of them are are much more stable in retention time more easily than others, and so there is sort of this internal distribution of retention times that you're always happening on. And it turns out that the IRT method gives us, no matter where we measure on that distribution, we end up with less variance in subsequent measurements than most other like predictive measures. But yeah, it is true that like if you were to measure 5 or 10 times and use a mean, you would get a more accurate IRT, and Skyline actually supports that. So if you wanna load in 5 runs of everything and get the retention times for all 5, and then calibrate based on that, Skyline will use the mean of those times. And that would be your most accurate. But
but if it's a variable peptide anyways, then also in your measurement it might move out again. So
well, but you're still, a mean is still you still want the mean. It's your best possible value. Yeah. It turns out in most cases it's not really that big a deal, and in fact, like we start with IRTs that we get from spectral libraries, which is again, where that's not even always consistently the apex of the peak, right? You get a spectral library, a spectrum might be measured, on various points on the peak.
I mean, usually in DTA data, a spectrum is triggered already maybe here, So here you have the MS2 spectrum. So the identification and the retention time will actually not come from the apex of the peak, but actually was triggered here, so you would predict the retention time if everything was stable. So these are the things but also Ludovic, the Thursday is going to discuss some of these issues in the library generation lecture.
But really, I think in our experience, this IRT, even when you do it several times, you should expect, I mean, of course it also depends on the gradient length, the longer your gradient, the higher the variability, I also think. But if you see that your peptide is jumping by 2 minutes back and forth when you do 2 or 3 replicate repetition injections, I would be very suspicious what's going on. We don't see this. We're talking about really everything below 20, 30 seconds maximally what you see in variation. It's working quite
I mean, for me, so I did this, I injected these pools of 100 peptides, 100 synthetic peptides just. And in each of these 100 synthetic peptides, I added the 11 IRT peptides. And I determined, like this, with shotgun, I determined the retention time. And I mean, this was from water and 100 peptides derived retention times. And it still worked very well. So I converted from there to IRT, and then I used these IRT values later on in my whole cell lysates. And it were, I mean, yeah, as said, I used these plus minus 2 minute windows on a 35 minute gradient. So my total gradient was 35 minutes. So actually, my windows are kind of large. So I have 4 minute windows. But that worked very well, even though it was determined on synthetic peptides in water and afterwards used in whole cell lysates. I mean, for most of them. Yeah.
So if we are using these IRT peptides in our sample, I think we don't need to use the synthetic peptides for absolute quantitation peptides. Because I think the heavy peptides are used in absolute quantitation to see that, okay, my sample peptides are exactly eluting at the same time. I mean, the retention time are same.
So this whole concept has nothing to do with absolute quantification. No correlation at all. Here we're talking about retention time.
The thing is, maybe I can say, so far, so heavy reference peptides are not just to find, they of course help us to be sure that this is my peak, because this is the heavy, and this is my endogenous, so the light. And the heavy helps me a lot to find that this is my true peak and not this one or this one. So it helps in the confidence, but mostly we spike in the heavy reference peptides actually. And are you going to talk about this, or we have the tutorial also? The heavy references are usually used to calculate the abundance. So if I know I spike in, 100 femtomole, I will know that my peptide, which has half the intensity, will be 50. That's the main purpose of using heavy reference peptides.
Isn't it also a question of ionization factor? Because you need to have the same sequence to get the same ionization factor.
The heavy will always be the same.
Yeah, to have the absolute quantification. Because I guess if you use another peptide of another sequence, you won't have the same ionization factor. So it can impact your quantification.
But usually, so the IRT peptides are completely separate of absolute quantification. We will also do this in the tutorial. You basically, then you can only do relative quantification. So in one sample it's this, in the other it's this, and then you say, okay, that's 2 times up. But this will all be discussed.
Is there a need to make this IRT checking time retention for, let's say, for sampling a few conditions? So do I have to make this correlation for every of experiment conditions? So do I have to spike on this IRT for any condition in an experiment, or just for this, let's say, to calibrate?
Yeah, it's true. if you think they're kind of expensive or so, I mean, you don't need to spike them into all. We spike them into all our samples, and you can also. Yeah, I don't repeat the calibration. I just spike them in, and as a quality control kind of. For us, it's a lot. Also, there's a lot to do with quality control. But it's true that it's not necessarily required that you have them in all your samples. But every now and then it might be good to check, and in case you want to recalibrate, that you have them in. And maybe in that.
Do you see any kind of ion suppression in the areas where the IRT peptides are eluting?
I haven't looked for it.
You don't spike them in the picomolar.
Okay, so which
you
is
still spike them in a
femtomole.
concentration similar also to.
So 100 femtomole or much?
I think
Less.
probably.
We actually
less.
don't know. We just know 1 to 20.
So you get them and you make a dilution, but it's not an incredibly crazy peak. It's a nice.
So it's in the range of the same peaks that you're.
Yeah, I mean, if you think it's too high, you dilute it a bit and spike less.
Yeah.
Yeah.
It's a good point. You should not make it too high, but it should be nice. Maybe one more comment to the should I have them in every sample or not? Because if you want to use Skyline to analyze your sample and to set up the IRT setup as you will do later and as Olga has shown you, and if you want Skyline to be able to show you for every sample this predicted value and the shadow around it, you need to have it in every sample. Because in the moment when Skyline doesn't find in a certain sample the IRT peptides measured, it cannot make the calculation and it cannot make the prediction for this sample. So it is definitely, if you want to have this cool feature, and I think it is really great, especially when you start working with data-independent acquisition, for every new sample that you load, you want to have, again, shown what's the optimal value. And if you have small shifts between samples, Skyline can account for this by, for every sample, making this optimal calibration. And then you need to have it in every sample. So, and this is why I think it's recommendable to put it in every sample. And if you, this is why it might be also very interesting to not work with synthetic spike-ins, but to develop your own IRT with your endogenous samples. If you always work with the same one with this. It sounds, in the first time, sometimes a bit complicated, but once you did it the first time yourself, it's really easy and straightforward.
However, if it's only for the measurements and you calibrate it at the beginning of your samples, if the samples in complexity did not change, you would expect that the retention times in minutes should stay the same if the system was stable and everything was stable. So for the measurement, maybe you don't need it unless you change sample complexities considerably along your run. But afterwards, when you import the data, like Tina said, it will be useful to have them inside.
So with the IRT peptides, you mentioned earlier that the IRT value is very stable, right? But you just mentioned that for your sample, it jumps around sometimes. And then, it wasn't mentioned you can use the endogenous peptide as the standard, but how much can you trust the endogenous peptide if they can jump around?
I mean, the thing is that the peptides shouldn't jump around, so that's already very weird.
So that's the experience.
Yeah, but then, so I wouldn't take a peptide that jumps around as retention time peptide.
How do we know? Maybe under some conditions they don't. But say one day I change a column or something else, and if they jump,
I think the key there is work on your chromatography. What we discussed in the first day, that like people who have really good chromatography, their peptides don't jump. And
because I've never done this.
And the thing is also, I mean, we are not using 2 IRT peptides to calibrate, and if this jumps, then everything is off. But we use 11, and if one of them is an outlier, the curve will actually not change much. So maybe if you have very jumpy peptides, maybe you work rather with 100 IRT peptides than 11, so that if you have some outliers, they would compensate for each other.
I think my problem is just in the fact that I was trying to do this for a really huge data set and I think that if you do it, I mean, it was true for few peptides in my data set, so it could be some physical property, because I presume that IRT peptides, they didn't take some random peptides they actually selected them for like physical chemical properties and they show stable control.
And I mean, also maybe one important point, so if you have a modification on your peptide, this will change or might change also the retention time. So Tina and Ariel, you are going to show in the phosphor talk that we can actually, the phosphorylated peptides and the naked peptide can easily be separable by chromatography. So maybe it also has to do with modification.
Yeah,
Even though
maybe,
then you would be
yeah, I mean, I think it was just on my part, instead of taking select 10 peptides and do this, I've done it on 150, and then you obviously end up with a bit of a mess.
Yeah.
And give up.
150 for the standards, or no?
No,
for
just for targeted peptides in a single one.
You
So
should
it
be
can
able to
happen
do.
also
You should
that-
be able to do 150 with pretty stable.
I'm sorry.
Yeah, but maybe you have one peptide that is very high abundant, and then you don't reach the equilibrium in the chromatography.
Yeah,
or they elute very early
Yeah,
and
yeah.
also didn't
Yeah.
reach the equilibrium. So it can happen in some
Yeah.
cases depending on the concentration and in the physical properties
Yeah,
of the peptide.
Yeah, yeah.
Yeah, also in the beginning
If you
of the
have a very
gradients.
broad
Yeah,
peak
yeah.
and very high abundant, then probably if you inject again, the retention time is not exactly.
Yeah, and in the beginning of the gradient, it's true there the retention times are shifting much
So
more.
it depends, yeah.
Yes? Oh. Sorry, maybe you can go first.
Yeah, do you use the IRTs also for quality control of the emitters? So you look at the
Yeah.
sensitivity and temperature?
Yeah, exactly. Yeah, because it's nice because you spike them into every sample at exactly the same concentration, obviously. So you can nicely monitor if your system is going down. Or also, what is interesting because they span the entire retention time range. For example, on the triple top, we sometimes have charging, which only affects like the second half of the retention time gradient. So we see that the early retention time peptides are stable, but the late eluting retention time peptides go down. So it's actually quite nice to get a feeling for your runs, especially if you run dozens of samples over time. Yeah.
Just to confirm, so you spike it, the IRT peptide in 1:20, is it?
Yeah.
20 times dilution.
Yeah.
Unlike what is stated in the manual from the producer.
1 to
so
10.
Yeah. So
It's
it's 1 to 10.
1 to 10 is recommended, and we use 1 to 20, which is fine.
And you can use it.
And you can go lower,
Okay.
but yeah. I mean, you just at one point you want to be sure. I mean, it's annoying if you have to correct and look for the retention time peptides. So
Especially
spike
when
them
you
in
start
too
working
high.
with automated tools, and especially when it comes to swath, so many of the software tools around can do this all automatically. IRT reading and doing these calibrations. And the moment when the tool can make a mistake because the peak is too low quality, everything is screwed. So you want to make sure that every tool is really able blindly finding these peaks. So it makes sense not to make them too low.
Yeah.
With the care.
It's possible to work with concave quadratic gradients as well, or just linear gradients.
We don't have experience with this. But do you have experience with non-linear?
Here it's linear regression, but in theory, if you would do a regression in, am I correct, Brendan? Skyline only does a linear regression. So
But I
there are
think
no
he's
other-
talking about the gradient,
gradient, not the
about the regression.
Yeah, but
But
Yeah,
the gradient,
Okay, wow.
the regression is linear because the gradient.
Yeah,
is
yeah,
linear.
yeah, yeah,
So
yeah.
you would need a different type of regression if you have a different type.
Well, I mean, yes and no. It's based on their relative position, the position of the peptides relative to each other, and how they come out. So yeah, a nonlinear gradient would actually, like, it might have shifts different in different parts of the gradient. So then the shift wouldn't be linear, but I think it would actually probably work reasonably well
I would also
with a linear regression.
Because the order of the peptides remains the same, and your target peptide will always elute between retention time peptide 7 and 8, let's say. And even if you change the slope of your gradient, it will always be eluting between, or hopefully always be eluting between retention time peptide 7 and 8, even if they are more or less apart from each other.
You have to recalculate the IRT value.
Yeah.
Because I understood
I
what
think
happens
it's
if you have
different if you
two
have
slopes with
exactly
different,
if you
with
have two slopes like this.
different gradients, two different gradients,
Two different
slopes in your
gradients.
setup, right? Or did you mean this or?
The IRT value is going to change as compared to a completely linear gradient. You just have to inject them again and recalculate those values and then calculate that for your samples.
For example, if you're analyzing 10 very hydrophilic peptides and one very hydrophobic, so we use quadratic gradient to separate the well and accelerate the recognition of the last one.
This is what I mean. So you will have a change in your gradient slope in your gradient, and I would assume you would need to do the same then in your IRT calibration to be as accurate as possible.
To be as accurate as possible, but really it's just a proxy for the order of elution and the sort of relative distance in elution time that they have from each other. And so only if there is a different change in these two so yes, if the relative times can change differently if there's like a change in the two different slopes, but I think fairly frequently that a linear gradient would work a linear regression would work just fine. But so your regression doesn't necessarily have to match your gradient. Is what I'm saying. It's like,
I guess it also depends how different the slopes are you're talking about. Has to try.
The answer is try.
Yeah.
Let us know though.
Yeah. For sure, it will not possible in Skyline to adjust two different slopes. Also, I need to do mathematically. No.
Schubert kind of does linear regression.
There's linear regression. That's the definition of IRT.
So then we stop for lunch, I guess? Or?
Yes.
Yeah. Okay, so